Okay guys, so this video is going to be a real quick one about KC, okay? There's a bit of an organic knowledge thrown in here as well. Not too much, so it shouldn't be too difficult. Now, this is from an A-Level Chem paper, okay? Past paper 2, June 2017. So if you want to check it out, attempt it yourself, see how you do. Practice makes perfect. We're coming up to paper 2 and 3, so best of luck to you guys out there. Now, let's jump straight into this. Question 5. Ethanoic acid and ethane 1,2-diol react together to form the diester C6H10O4 as shown. So we've got this nice equation going on. Draw a structural formula for the diester C6H10O4. Okay, so what's going on here? We've got an esterification reaction. Very simple stuff here. So we've got anytime you react a alcohol and carboxylic acid, you get an ester forming, okay? So considering this is a di-alcohol here, this is essentially going to be in the center. Okay, now on either side of this, we're going to be getting the carboxylic acid portion, which makes up the ester. Okay, hopefully you're aware of this. So what I'm going to do to make things a bit simpler is I'm just going to draw the central CH2 with the O's as well, and then draw the carboxylic acid off of that. So CH2, and then what we can draw here is we can draw the O's. Okay, and then branching off of that, I'm going to draw our carboxylic acids. So carboxylic acid, H3C, and then down here, I'm going to draw our CO. This is a bit of a weird molecule. I don't know why I drew it this way around, but essentially, as long as you draw it structurally and you get all the correct molecular formula here, you'll get the mark. Okay, so let's just double check that I did it right. 1, 2, 3, 4, 5, 6. 3, 6, 10, 04. Yeah, all good to go. Okay, this was an absolute shambles, but hopefully you understand what I did here. Normally the way I like to do is I like to branch off the carboxyl group like this, going up and down from the carbon due to the double bond here. But however you do it is completely fine. Okay, with that embarrassing drawing out the way, let's go on to 5.2. A small amount of a catalyst was added to a mixture of 0.47, let's get me highlighter right here, 0.47 mole of ethanoic acid and 0.205 mole of ethane 1,2-diol. The mixture was left to reach equilibrium at a constant temperature. Okay, so they've laid this out in a nice table here for us, okay? So normally what you have is you do ice tables, okay? Ice tables, in my opinion, you can do this however you want. Ice tables, in my opinion, are the way to go. So I being initial moles, C being change in moles, E being equilibrium moles, okay? So they've sort of done the I and the E for us already, so I'm just going to chuck in a C here, okay? I'm just going to call that delta for a change, just to make it a bit quick on the notation side of things. So what you have to do is just do 0.47 minus 0.18, and that is going to tell us the change in moles for the ethanoic acid, okay? So let's do that right here. 0.47 minus 0.18 is going to be 0.29, okay? Now, what we have to do here is we have to look at the molar ratios within the equation. So our ratio up here, if I scan to the top, is 2 to 1 to 1 to 2, okay? So what that tells us then is, they haven't given us any other variables, have they? No, okay. So what that tells us then is that this change for the ethane 1,2-diol is actually going to be half of this. Hopefully that makes sense because it's a 2 to 1 ratio. Okay, so I'm just going to write that as 0.29 over 2. Okay, so if we do that in your calculator, you do 0.205 minus this divided by 2, it's going to give us 0.06. Okay, I'll add an extra 0 in there in case they're weird with the sig figs. Now, when it comes onto the ester form, the diester and the water molecule, the change is going to equal the new moles, okay? So if you do this 0.29 divided by 2 as an actual decimal, it would be 0.145, okay? Now, that's going to be our answer here for the diester. Now, for the water, again, because it's a 1 to 2 ratio, you can just double this up again, which is exactly the same as the ethanoic acid. So I'm just going to put in our 0.29 here. Okay, 3 easy marks right in the bag here. Okay, 1, 2, 3, not too shabby. So 5.3, let's look at this question here. Write an expression for the equilibrium constant Kc for the reaction. The total volume of the mixture does not need to be measured to allow a correct value for Kc to be calculated. All right, interesting. does not need to be measured. All right, so we have to justify our statement. So the expression, okay, KC, super easy. Concentration of products over concentration of reactants, and then you got to chuck the molar coefficient to the top right of the square brackets. Hopefully that makes sense. Let's draw that in right here. So KC equals product 1 is going to be a diester, so C6H10O4. And then the moles are just 1, so I'm going to leave it as it is. Then water, H2O, with squared, because it's got 2 as the molar coefficient, divided by our ethanoic acid, CH3COOH. Square that guy up, because it's got a 2 mole coefficient. And then we've got our diester, dialcohol. Okay, so ethane, so HOCH2, CH2OH. Okay, no reason to square or anything here, no power required because it has got a mole coefficient of 1. So that's out of the way, not too hard. Hopefully you guys are completely fine with KC expressions, pretty simple. Now, when it comes on to the justification, this is where it gets quite interesting, okay? Now, you can make this assumption and do this in a lot of calculations. If you're advanced with maths, your eyes may just pick up on it straight away. But in the case of chemistry, okay, so and I changed my color up to a nice red here so we can sort of expand upon this. Now, how many concentrations are on the top if you take into account the powers? Okay, you may be like, what the hell is he on about? But I'm going to explain myself. So on the top, we've got 1 concentration here and 2 concentrations here. Okay, concentration variables, as it were. So I'm going to just put a 3 here, okay? And that's divided by how many concentration variables on the bottom? 1, 2, 3. Okay, so we've got the same number of concentration variables on the top of the equation, on the top of the fraction, I should say, and the bottom, okay? So if we think back to our mole equations, okay, N equals CV, hopefully this is known off by heart to you guys. If we rearrange this guy to make concentration the subject, it's simply going to be C equals N over V, okay? Now, what we can do is we can actually convert these into our N over V. So what we would have ultimately is 3 lots of N over V and 3 lots of N over V on the bottom, okay, on the top and the bottom. So although the moles are different, like we can see here, at equilibrium, all these moles are different, okay? The volume, or the total volume, I should say, in the beaker or whatever we're looking at, is going to be exactly the same. So it's going to cancel on the top and the bottom of the fraction. Okay, so whoop, whoop, cancelled out completely. So we can actually, don't even have to do concentration for this. We can just use our mole values and plug them straight into the expression, okay? So that's what I would say here, is that when the number of moles are equal, the mole coefficient is equal on both sides. So you've got 3 moles total here and 3 moles total here on the reactants and the products. When they're exactly the same, you can cancel it out, okay? So that would be my justification right here. Okay, number of moles on each side of the reaction are equal. Easy as that. You don't need to do all this explanation here. That was just for you guys. So next question. A different mixture of ethanoic acid, ethane 1,2-diol, and water was prepared and left to reach equilibrium at a different temperature from the experiment in question 5.2. The amounts present in the new equilibrium mixture are shown in table 2. All right, so we've got a nice table here of new moles. The value of Kc was 6.45. Use this value and the data in table 2 to calculate the amount in mole of ethanoic acid. Give your answer to the appropriate number of significant figures. Okay, really important. AQA loves to see this. Okay, so essentially all we have to do here is look at our Kc expression, rearrange it to make ethanoic acid the subject, but they are looking for the moles rather than the concentration. But what we can do here is we can take the assumption that we did in question 5.3, and then ultimately, because we're not given any volumes here, we can just assume that the total volumes are going to cancel, and then we can just use the moles straight into the expression. Easy peasy, let's go. So what I'm going to do is I'm going to write everything out, so all our variables out, with the original Kc expression, and then just rearrange it, and then hopefully you guys can follow along. So it's going to be our 6.45, that's our Kc value. Okay, so it's going to be 0.802, and then our water 1.15. Okay, square that guy up all over. Now it's going to be our calculated value, so I'm going to put CH3COOH. Now, ultimately, these should be in square brackets, okay? But we don't need to do that because we can just assume that they're moles. Okay, we don't need to show square brackets here, okay? Even though you do really need to show it up here for the Kc expression, because we're assuming that the volumes cancel, you can just leave it as rounded brackets for moles. If you're extra stressed and worried, you can always just chuck in the square brackets if you really want. But yeah, it doesn't really make sense. So what else have we got here? Our other reactant, 0.264. Okay, now I left off a square here, so that's going to be really important because when we make this guy the subject, we're going to have to square root everything. Okay, so if I rearrange this real quick, what it's going to be is simply our concentration or the moles of ethanoic acid that we're looking for, and you just have to swap that around with the Kc. Okay, if you're not that used to rearranging, you can easily just swap them over. Okay, that's a little shortcut right there. So this is going to be CH3COOH equals, now because this is ultimately squared, like I said, we're going to have to square root everything, so I'm going to do that right here. Square root 0.802 1.15 squared all over our Kc, so 6.45, and then our 0.264. Okay, hopefully that makes sense, not too complicated. Now if you put that in your calculator, you're going to get an answer of 0.7892. okay, but what sig figs do they want here? Okay, now 3 sig figs, 3, okay, so ultimately, and also this guy right here, the 6.45 is also 3, so I'm going to have to put my answer to 3 sig figs, so to 3 sig figs, 0.789, easy marks in the bag. Okay, so not too bad here, got 1 mark, 4 marks, 6 marks, 9 marks in total, right? Not difficult questions if you just learn the fundamentals of Kc, Equilibria, working out using the ICE table. We didn't have to do it here because fortunately AQA sort of made the table for us. But that would be my approach normally. And then just learning that with fractions, okay? When we've got N over V, on the top, the variables of volume can cancel. And then just typical rearranging equation here, not too complicated, okay? Now, hopefully this video was helpful. That's the end right here, okay? So if you did find it helpful, if you did learn something, be sure to like the video. It really helps the channel grow. Subscribe for future maths and science content. Best of luck in your upcoming exams, guys. Peace.